Okay, good morning. We'll go ahead and get started. Some of your classmates may have not seen the email that I sent out. So if you want to share with them that we are having the lecture via Zoom, that'd be great. And also, I have posted the attendance code in the chat and share that with anyone who may be joining a little later as well. Um, Today, I'd like to back up a little. First of all, welcome you all back from spring break. I hope you had a great break and a restful break. Um, I'd like to back up a little and go back over a topic that we touched on, but we didn't go into a lot of detail on, and that is line balancing. And before I delve into that, I'd also like to make an announcement. I do have a plant visit scheduled for an industry sponsor on Friday. So instead of doing the lab on Friday, my plan is to have a lab on Wednesday during our normal class session. And that lab on Wednesday will be pertaining to the subject that we cover today, which is line balancing. It will be in the classroom, and I will get more information out to you on that and make it accessible through Blackboard. Also, today's lecture is not in Blackboard yet, but it will be following this Zoom presentation. I had some technology issues, but I've gotten through them and should be able to make this lecture available to you later today. But having said that, let's go ahead and get started. Again, we're talking about line balancing. And when we're talking about line balancing, we have to understand that engineering oftentimes means that we're dealing with messy and unpredictable work environments, and we're trying to take that messy, unpredictable environment and work that into some type of organized system. Hence the saying industrial and systems engineering. So in manufacturing, especially when we're dealing with mass production, there are dozens of tasks that must happen in the right order and at the right speed. So that doesn't happen without coordination. And if we don't have the proper coordination, workers tend to move at different speeds. And what that does in a mass production environment is it causes bottlenecks, idle time, or even wasted effort. So we look at line balancing, and line balancing is the mathematical approach that helps us to organize these different tasks so that the work flows smoothly through the system. And the goal of line balancing is really simple. We just want to divide the work among the workstations such that we keep each worker busy and we maintain a steady production rate. And so you can think of this as engineering order out of chaos. So we're taking a lot of different independent human actions, machine actions as well, and turning them into a well-oiled machine, into a synchronized production system. So over the next few slides, what we'll look at is how assembly lines work, why line balancing matters. We'll look also at some of the calculations that we use as engineers to design an efficient production line. And by the end of all this, you'll see that line balancing is really just about matching the work content to the time and resources that are available to keep our production moving along as efficiently as possible. So modern manufacturing does rely heavily on assembly lines. Almost every mass-produced product that you can think of that we use today, whether it's cars or laptops, smartphones, appliances, every product you can possibly think of is built this way. So an assembly line breaks a complex product down into a bunch of smaller tasks. And each one of those tasks is performed at a workstation along the assembly line. So instead of one person building the entire product, we've got multiple operators who work sequentially, and each one completes part of that process. So you can think of the assembly line as a team that's working in sequence. Each worker passes a partially completed product to the next workstation. And because all of the stations are connected, the overall production rate in an environment like that is controlled by the slowest operation, which we call the bottleneck. And if one station takes longer than the others, then the upstream workers may finish early and they're waiting on parts, or the downstream workers may run out of work. That's why planning and task assignment are critical. And the goal that we want to achieve as industrial and systems engineers is to distribute that work so that every station operates as evenly as possible. And this planning process, deciding how this work should be divided among these different stations, is exactly what we call line balancing. And one of the most important concepts in production systems, as I mentioned, is the bottleneck. So when we have an assembly line, the entire system moves at the speed of the slowest operation. Now, it doesn't matter in that setting if the other workers are faster. The slowest task will always determine the output rate. So you can think about this simple example that I'm displaying on the slide. You've got a worker, worker A, who completes a task in 30 seconds, but worker B takes longer. Worker B takes 60 seconds. And even though worker A is twice as fast, that product cannot move forward until worker B completes their work. So what happens during that extra 30 seconds? Well, worker A essentially has nothing productive to do. They're simply waiting. This is what we call idle time, and it represents lost efficiency in the system. So in reality, faster workers often slow their pace down naturally. It's just human nature to match the bottleneck because the flow of the parts forces synchronization in the process. This is exactly the problem that line balancing tries to solve. And how does it go about it? In line balancing, again, we want to redistribute those tasks and even out workloads across all the different workstations within the process. And we do that such that we minimize the idle time. We minimize the amount of time we have workers who are waiting. When the work is balanced properly, then each workstation finishes close to the same cycle time, and that allows for our line to flow smoothly. Now that we've talked about this bottleneck problem, let's look at this concept a little closer that we're putting in place to solve it, line balancing. So line balancing is the process of determining the ideal number of workers, and how tasks should be assigned across a production line. So, in other words, we want to distribute that work so that each workstation has roughly the same amount of work to perform. And why is that important? If one station has too much work, then it becomes the bottleneck. And if another station has too little work, then that worker spends an inordinate amount of time waiting or being idle. And the goal is to balance the workload so that all those workers finish their jobs at approximately the same time each cycle. And when that balance is achieved, again, the products are going to move more smoothly through the process. um, Idle time will be minimized, and throughput and efficiency of that production facility is going to increase. So in practice, line balancing involves us identifying all of the work elements involved in producing a product, determining the proper sequence or the precedence that they must occur in, calculating the cycle time, and then assigning tasks to workstations efficiently. So we're going to look at that over the next part of the lecture. We're just going to walk through how engineers actually perform those calculations, and they design what we call a balanced assembly line. Now, when we talk about balancing a production line, we're usually talking about four basic steps. The first step is to list all of the work elements that are required to build that product. The second step is to identify the precedence relationships between those work elements. Which task must happen before others? And then thirdly, we want to determine the required production rate, a production rate which ideally lets us calculate the cycle time. And then finally, we want to assign the task to the workstations so that each station's workload stays within that cycle time we've established and the line flows smoothly. Now, line efficiency, that measures how much of the available time is actually used for productive work. Because workers must wait, as we said, for the slowest station, some time is lost. And this is what we call line delay. So we have an efficiency formula that we can look at. And that efficiency formula is the sum of the standard minutes for the assembly of the product divided by the sum of the allowed standard minutes. And we usually multiply that times 100 to give us a rate or a percentage. So as we look at this particular example, we've got work content that if we add up each one of those standard minutes, then we have 2.07 minutes. And that's simply the sum of this column here. Let me see if I can annotate. Yes, that's simply the sum of this column here. And then we also have the available time. And if we look at that, that's the allowed standard minutes. That's this column here. So we have 2 minutes and 2.07 minutes, which is the standard minutes, the sum of those standard minutes, which is our work content. And then we have the available time, which is 2.4 minutes, which is just the sum of the allowed standard minutes. So once we perform that calculation, we have an efficiency rate of 86.25%. That means that the remaining 13.75% is what we call idle time. And that's caused by an imbalance in our assembly line. So let's talk a little about some vocabulary involved. So there's some key terms we do need to define. And the first of those is what we call a work element. And that's just an individual task that's required to build any product. Then we have a workstation, and that's the physical location where we perform those tasks. And then, of course, we have the precedence, and that defines the required order that those tasks must occur in. Some steps, as we said before, must happen before others. So line balancing is about assigning those work elements to the workstations while respecting the precedence constraints. So you can see that depicted in this diagram here. So cycle time is the maximum time that's allowed at each workstation to meet demand. First of all, we calculate the required production rate, which in this case is about 53.3 units per hour for 100,000 units per year. And you can see how that's calculated. You have a demand in this case of 100,000 fans, and the available time that we have to work on those fans, 50 weeks. Of course, we're allowing for a couple of weeks of vacation, but we have where the plant actually shuts down. So we've got 50 productive weeks. We work 5 days out of those weeks, and we work for only one shift or 7.5 hours per day. So if we simply do the math, That's where we come up with the 53.3 units per hour. So we look at our cycle time is equal to 60 times the efficiency divided by the hourly production rate. So here we plug and chug, and we've got our cycle time is 60 times 0.96 divided by the 53.3 gives us 1.08 minutes. So that means that every 1.08 minutes that a finished product must come off of this line so that we can meet our annual demand of 100,000 fans in our assembly line. So one common method that we can use for balancing assembly lines is what's known as the ranked positional weights methods, or RPW. Now, each task is assigned, in this case, a positional weight, which equals to the task time plus the time of all the tasks that must follow it. So, for example, task 12 has a weight of 0.12. Task 11, if we look at it, becomes 0.62, and task 10 becomes 1.0. That's because we are summing the tasks that must occur after it. So after ranking these tasks by positional weight, we can assign them to workstations while respecting the precedence that they must occur in, and also the cycle time constraints that we have calculated. Now here's an example of line balancing using a small product assembly. So the table here depicts 12 work elements and the time that's required for each one of those tasks. So you can see those 12 work elements are listed here, and the task times are listed in the adjacent column. So for example, work element 1 takes 0.3 minutes, work element 2, 0.25 minutes, and so on until you get to work element 12, which takes 0.4 minutes. So if you look at summing all of the tasks or work elements that must occur in the assembly of this hypothetical fan, then we have a 4-minute process. So the labor content of one fan in this case is 4 minutes. And that again is the sum of adding all of the task times together. And so that represents again the total labor that's required to build one unit or one fan. So next, what we'll do is we'll use this information with cycle time and the precedence relationships that we've talked about to determine how those tasks should be assigned to the workstations that are available. So we can estimate the minimum number of workers that are needed using the total task time and the cycle time. So the formula is this: the minimum number of workers is equal to the total task time divided by the cycle time. So in this example, we have a labor content of 4 minutes. We've already calculated it takes 1.08 cycle time for this particular assembly. So that will yield 3.7. We know we can't assign a fraction of a worker in this case, so we would round up. So that means that we need at least 4 workers for this process. So with a cycle time of 1.08 minutes to produce that 100,000 fans that we need to satisfy our demand, about 1 minute is actual work, and the remaining time does account for movement between stations. We can visualize this using a precedence diagram. And this precedence diagram helps us to understand the order that the task must occur in for this assembly process. So each node or each circle in this case represents a work element, and the numbers show that are above each node the task time. The arrows indicate the precedence, meaning one task must be completed before the next one begins. So some branches show parallel paths where tasks can occur at the same time. And we look at diagrams like this to help us see the workflow rather clearly before we assign tasks to different workstations. And you can see the precedences in this case uh, that these operations must occur in. For example, we've got task one with a time of zero point 0.2 minutes that must occur before 3:04, where 3 has a time of 0.7, 4 has a time of 0.1. And you can see also that task one can occur or does occur in this case in parallel to task two. Now to manually balance a line, again, we use this RPW method. It's one method that we can use. There are others, but this is one of the ones we'll focus on in this class. So RPW is used to prioritize which task should be assigned first. So the positional weight equals the task time plus the time of all the tasks that follow it in that precedence diagram that we just looked at. So the task with a higher RPW, those are the tasks that are more critical in our line balancing. So they are the ones that we want to assign to workstations earlier. So this helps us to make sure that those important upstream tasks don't become bottlenecks later in the line. So we can calculate, in this case, let's say we want to calculate the RPW for element one. The way we would do that is we would start with the task time for element one, which in this case is 0.2 minutes. Then we would add the time of all the tasks that follow it in the precedence diagram. And if we look at the tasks that follow it, we would see that those tasks are given to us as 3, 4, 6, 7, 8, 9, 10, 11, and 12. Now I have a question for you. Why wouldn't we include task 2, for example? Even though my slide in bullet 3 says task 2, that actually is an error. So I've caught an error in my own slide. I'll have to fix that before I post this. If anybody wants to come off mute and give what you think is the reason for that, why wouldn't we include task 2, for example, in computing the RPW for element 1? Okay, I'm starting to see responses in the chat. That's allowable as well. It's bigger. It's bigger than the first task. Okay, that's a good guess. Anyone else want to offer an answer to why we would not include, and I do have an error in my third bullet, Um, and it's kind of a clue. And I'll go ahead and um, give you the answer to that. Really, when we're looking at task two actually occurs in parallel to task one. So it doesn't actually precede task one. And likewise, if we're not pursuing task two, you can see a relationship between task two and task five. If we're not pursuing task two, then we're also not pursuing task five. Neither of those will be necessary for us to calculate the RPW for element one because they actually do not follow element one. So I'll fix bullet three, and you can see the math there for calculating the RPW. And if you calculate the RPW for task one, that becomes now 3.3. And you can convince yourself of that in your own time, but once we calculate the RPW for each one of our tasks, then the next step would be for us to rank them from highest to lowest. So as we calculated, the highest would be for work element or task one, which has an RPW of 3.3. So it's the highest. So it would be first in our ranking, and we want to make sure we assign it to a workstation early. So when balancing a line, we would select the task from the top of this list. So starting with work element one and work our way down. And that way we're respecting the precedence and the cycle time limits. So you can see that how that's done. So the next work element, for example, would be work element three, which has an RPW of 3.0. Then element two, which has an RPW of 2.67. And again, you can work through that on your own and convince yourself of the accuracy of these calculations. And then after we have ranked our task by RPW, we can begin assigning them to workstations in order. So we would move down that RPW list, adding task to the current station. And the key constraint is that the total task time cannot exceed the cycle time limit. So we've got about, remember, 1 minute per station, which we calculated earlier. If we take away or remove the travel time from station to station, we have about 1 minute. So if we're adding these tasks that would exceed the limit, then we need to skip it, move it, or move it to the next feasible task. So for example, station one has a work element there that takes 0.2 minutes. Then we have work element three has a time of 0.7. That yields a station time of 0.9. We wouldn't add the next work element because that would push us over the 1 minute cycle time that we need. We would then move to uh, work element two to the next station and continue the process. And you can see workstation two, we have 0.91 as the station time there, and that's simply the sum of those times here. And then workstation three, four, and five. And this is how we would go about assigning workstations. Now, after assigning these different task stations, then we can see how efficient our line is. So any unused time at a station, we call that a line delay. So of course that represents for us in this instance lost productivity. So not every station is going to perfectly reach that 1 minute limit. As we saw, we didn't have any that perfectly reach that 1 minute limit. So there's some idle time that's going to be expected, but we're trying to minimize that. So the allowed minutes are determined by, again, the bottleneck station, which sets the pace of the line. So we calculate efficiency as the sum of those standard minutes, as we did at the beginning of the lecture, divided by the number of stations times the allowed minutes that we calculate. And that efficiency formula is given for you here. And when we look at that, our total standard minutes is 4 minutes. But our actual stations, when we look at after assigning all these tasks, we can evaluate this final balance. So the total work content again is 4 minutes, and the solution required us to have 5 stations. So the bottleneck station is 0.92 minutes, which sets the pace for the line. And we saw that earlier here. That's where we get the 0.92. And we can see that's at station 3. That's our longest process or longest time for our different stations, the 5 stations that we needed. So now that we have our bottleneck station of 0.92 minutes, setting the pace of that line, we can use our efficiency formula, and we come up with about a 87% efficiency, just plugging our numbers. And so the question we want to answer for ourselves is 87% good enough? Or should we rebalance this line? Should we try and do even better? And we accept that 87% if a current demand is met and if it offsets a relatively high cost of redesigning our workstations, because that work does cost the company something to do. And we rebalance, and if we want to rebalance, on the other hand, we have to think about the fact that labor is expensive and that the expected future demand increase may require some new machinery. And in that case, we may need to look at rebalancing our line. So how do we go about this line balancing? This slide summarizes our overall workflow that we would use if we want to look at a line balancing problem. So first of all, define all of the work elements and record their different task times. The next step would be to calculate the cycle time based on the required production rate. Then we would draw our precedence diagram to show the order that our tasks need to occur in. Then after that, we would apply the RPW method to prioritize and to assign our different tasks to workstations. And then finally, we would evaluate the efficiency of the line and check for any bottlenecks or improvements that may be possible. Okay, that's all I plan to cover for today. And again, looking ahead, as I mentioned, I do have a potential industry sponsor visit on Friday. So we will not have a lecture or lab on Friday, but on Wednesday, we'll devote Wednesday in class for our lab. I say 90 minutes for the project, or we may be able to do it within the hour. I'm thinking we may. And our goal during that lab, we're going to do a lab exercise on the content we just covered. So you'll find cycle time, the minimum number of workers that are required, and you use RPW to balance a line. And I'll give you a scenario, so I'll post this to Blackboard. It'll be a small electrical appliance assembly. And the specs of that is we're trying to produce 250,000 units per year. We've got 250 days that we can work out of that year and 23 hours per day. So in this case, we've got more than one shift. There's some constraints involved. There's an efficiency factor of 0.96. and we've got a minimum repositioning time from workstation to workstation, or task to task rather, of 0.08. Again, I'll post this to Blackboard, and we'll work on this in class on Wednesday as a laboratory exercise.